Hello, the internet. Welcome to another video. So this video is about an art thing. It comes in this little kind of IKEA picture frame box. The title is Flame Effect from 2014. This was one of those little projects that you do just to kind of blow off steam when whatever it is you're supposed to be working on isn't quite working out. It's mostly just one of these kind of novelty flicker flame bulbs that you'd usually use to, to kind of simulate candlelight, sort of. I just want to make something. So I build weird toys sometimes when I just have parts laying around. As the objects kind of bounced around and recombined on my desk, they eventually turned into this contraption with a printer stepper motor and a backlight inverter and one of these novelty bulbs. So now instead of giving you like 10 volts AC or so, like you would get directly from the motor, you get some hundreds of volts AC through this little step-up circuit that's mostly a flyback transformer. You can make little sparks, light up bulbs that you're holding. That was what originally inspired some experiments later with wrapping wire around these bulbs. I noticed that it was much more interesting when I grounded the bulb with my fingers kind of at the top, rather than just letting the electricity flow directly between the two plates. It acts a little bit more like one of those plasma globes than a normal neon bulb. This video is partly an exercise in how to capture this piece's effect photographically. It's actually simple enough that it'll be really easy for me to show you how to build one, but I think it's kind of a neat effect. I don't really want to take this one apart, but I have parts to make more, so let's build one together. So here's one of those flicker flame bulbs close up, and it's really put together much like a normal Edison base incandescent bulb. The two wires entering this glass envelope aren't connected by a filament. In fact, the two wires aren't actually connected at all. They lead to these plates that almost but don't quite touch. This flicker flame bulb is really just sort of a decorative surviving cousin of the original neon indicator lamp, which was super popular before LEDs almost completely replaced them. As we'll see soon, these actually have some interesting electrical properties that made them useful for analog circuitry as well. So much like the electric arc in this lighter, these neon bulbs rely on the properties of plasmas, gases that become ionized and can conduct electricity. In the case of this lighter, the voltages and currents are high enough to sustain a plasma in open air. In these bulbs, the combination of a low-pressure inert gas and closely spaced electrodes can give them a fairly low voltage, whereas this lighter might use tens of kilovolts. This neon bulb will light at only around 80 volts or so. Alright, so this here is my 1 kV mega ohm meter. If you haven't come across one of these devices, sometimes you hear them called meggars. They're basically multimeters. The real feature of a meggar is to be able to measure very large resistances by applying a fairly large voltage to the device under test. You can use it as a normal resistance meter, 0.1 mega ohms, otherwise known as 100K. It also read 150 volts, which is what it was putting across this resistor during the test. So I had it set to a maximum of 250 volts, but in that case it was also limiting it to about a milliamp, which is why we only got 150 volts across this. These things are mainly useful for testing for safety faults in, pumps and motor windings and all sorts of, household and industrial kind of uses. I have this one mainly for kind of isolation, transformer, safety kind of testing, but it's also a handy little neon light bulb tester. It reads 67 volts and 0 ohms. So that right away gives you a hint about the behavior of these bulbs. They are very nonlinear. They don't act like resistors at all. Right now, if you measured this with a normal resistance meter that didn't apply a high voltage, it would just seem like an open circuit. But after the glow discharge is started, and that is actually the technical term for it, then it's nearly a short circuit. And this is actually a negative resistance characteristic. It'll lead to kind of an avalanche of current. So in a way, these neon bulbs are actually kind of like LEDs, but with a much higher voltage and without the polarity requirement of an LED. To take a closer look at what happens when the glow discharge in this neon tube actually starts, I have it hooked up to both the resistance tester and the oscilloscope with a high voltage 100x probe. So when I do a 500 volt test, so the glow discharge phenomenon that these neon tubes use, it doesn't have as much energy as a full-blown electrical arc, but you do still have this mechanic where you need to put in a bunch of energy to kind of start the discharge, and then at that point it starts to conduct. So right here, once the voltage across the tube has climbed to about 85 volts, that reaches this threshold where it's enough for kind of a chain reaction inside the tube to start. And this chain reaction itself is kind of an interesting process. It's actually statistical in nature. The discharge doesn't just start spontaneously when the voltage across the tube reaches the threshold. There has to be some kind of ionizing event to get the tube started. This could be as simple as light rays coming in and knocking some electrons off of the cathode. So let's switch to a more convenient power supply. In this video, I'm interested in using these cold cathode fluorescent light power supplies. These are really easy to come by either online, on eBay, from surplus shops, or even just by taking apart old LCD monitors. Cold cathode light power supplies vary a lot, but you'll see the same parts in pretty much all of them. It's useful to think of them as kind of centered around this big high voltage transformer. Usually that will come with a healthy isolation gap. If you connected the CFL tube directly to the output transformer, it would be really easy to blow this thing out with too much current, since the tube will just continue to conduct. These high voltage series capacitors put an upper limit on how much current you can draw out of this transformer. So this one has a fuse, an input smoothing capacitor. There's a resonant oscillator comprised of these two transistors and the inductor. The output voltage will be proportional to the input voltage, and these modules will start at quite low input voltages of as low as a volt or so. It is important to hook up the input power with the correct polarity. In this case, the biggest polarity hint was the electrolytic capacitor here. If you follow its negative lead, it'll lead you right to the negative on the input. This is the smaller backlight power supply that I used on my motor toy. To save space, and because the input was already fairly low current, I removed the output current limiting capacitors on this one. And in this case, I'm powering the backlight inverter with fairly low current AC from this motor, and it's just dealing with it. This board didn't have any input filtering capacitors, but if you follow this input kind of around and under this sticker, it's shared with one of the outputs, which would really lead me to believe that this is ground, and that seems to work out just fine. Let's make this output a little easier to deal with. The transformer in a backlight power supply is like a small Tesla coil. It generates high voltage and high frequency AC. So I'm actually kind of squeamish about the prospect of hooking the scope up to one of these things unregulated, but these neon bulbs have the nice property of regulating the voltage, so it shouldn't get anywhere near the limit of what this scope can handle. So right now I'm only giving this inverter 0.8 volts, and the output is already about 100 volts peak to peak at 40 kilohertz. And if I slowly increase this, once it hits, there we go. So the input voltage hits about 1.8 volts, and then the output hits about, plus or minus 86 or so that's necessary to keep this neon going. And if I increase the voltage further, you can see the neon is acting kind of like a diode, just clamping the voltage right there. And all of that extra energy that would be going into increasing the voltage is actually just making the neon brighter. So quite quickly, actually, the input current rises as I turn up the voltage. This experiment with multiple neon indicators in parallel gives us some hints about what might be happening inside the flicker flame bulb. You can start to get a feel for how this is a random process by which they actually get started. Neon indicators are a little bit like LEDs. They don't glow at all until you reach this minimum voltage. But then after they start to conduct, they kind of hog all the current you give them. So normally you wouldn't want to connect multiple neon bulbs in parallel because they would share current unevenly. In this case, the LED on the right is hogging all the current. But if I introduce enough energy into this bulb to throw off some electrons, I can actually light the neon bulb with this laser. You could think of the flicker flame bulb almost like it's made of many separate patches of plate surface that are all connected in parallel. And all of those patches of surface are competing for current, and they all have these external effects like incident light and temperature that change the voltage that it forms a discharge at. With several isolated neon bulbs, the glow discharge can't move around. If the glow is allowed to fully extinguish and relight, it would come up in a random tube each time. This 50 kilohertz signal is high enough that the glow discharge never completely stops, so it just picks a random tube and stays there. This technique of storing information in the form of the location of a glow discharge actually used to be commonplace in computing in the form of the Decatron vacuum tube. This is a common xenon camera flash tube. It would require an extreme voltage to ionize the gas in the tube directly, tens of kilovolts. A low power but high voltage and high frequency pulse generated by a tiny Tesla coil style transformer causes a glow discharge through the glass envelope of this xenon flash tube. That glow discharge is enough plasma to cause the avalanche effect that then generates the higher current discharge across the length of the entire tube. Just like AC signals can pass through the dielectric in a capacitor, AC signals can cross through the glass into this otherwise sealed envelope. Just like on the smaller neon bulb, you can see a thin stem where two wires pass through the glass. In fact, we can even follow the wire from this front plate here, loops around under that yellow cement that holds the base on, and then it's soldered to that outside contact on the base right there. But the other contact goes down and presumably connects to this, but I think we're going to find a current limiting resistor in here if we open up this base. If you plugged one of these small neon tubes directly into mains power, once the glow discharge starts, the avalanche of current would quickly destroy the tube. But these are clearly designed to be run directly from mains, and I think the way they do it is by including a resistor in the base. It might involve breaking this piece on this black insulator piece on the bottom. Can't actually get any purchase onto there. I'm cutting right below where the cement joint is. You can already see the resistor. Let's get a closer look. Alright, there we go. So that resistor leg was just soldered directly into the base of the light bulb. So this outer surface here is actually the outer envelope of the bulb that's been glued to this metal. But then we have a little inner tube that actually carries the wires up to the point where they're sealed, right there in the base. And finally, in the very center of that tube, there's a really small tube that's been pinched off where the neon gas was actually filled. And just like we could see from the other side, one of those wires goes straight through the cement and onto this outer electrode. The other wire has just been twisted onto this kind of dirty little resistor. Wow, that value is a lot lower than I would have expected. 6.71K. Let's take that off. I think the resistor's just going to get in the way now. Just untwisting those wires carefully. Great. Now that we're rid of that pesky resistor, we can get an accurate reading of the voltage drop across this tube. 74 volts. All right, let's watch the voltage waveform on the scope when I give the insulation tester a go. Wow. In this case, we didn't start getting a glow discharge until the voltage reached 120, which seems pretty high. I wonder if the AC line voltage is just barely enough to actually trigger these tubes. After that initial spike of around 120 volts necessary to actually initiate the glow discharge, now we see the voltage across the tube fluctuate between 75 and 80 volts or so. All right, so this is a roughly 405 nanometer laser pointer. Without any bias voltage, we don't get any neon glow. To go get off there. So the laser isn't really doing much now either. My guess here is that the glow discharge is kind of too stable for me to just push it around with just the laser at this current and frequency. You see that? I can grab onto the neon. So this is a 405 nanometer laser pointer. It's actually pretty intense. Like, it's a laser pointer, but I still don't really recommend looking at it. But check that out. In some areas of this electrode, I can kind of grab bits of the neon and move them around with the laser. Yeah, I don't see the same effect with the 650 nanometer red laser. And this is the 532 nanometer green. Still don't really see anything there. That's great, I can just trap it there as long as I want. So I'm going to put this long, skinny inverter aside for later because it seems like a useful form factor for a different project. I think these might fit together pretty nicely. This one looks like it has kind of a spurious connector and some extra wires, but if you trace them on the back, it actually turns out that this blue and orange wire just go directly to this extra connector. So maybe that was like a button or an LED or something in the original product this came from. This one has an input filter capacitor rated for 50 volts, 47 microfarad. And just like on the other board, we can use that to verify the polarity. I'm going to start by just removing the unnecessary wires just to keep this clean. I'm going to take off this ferrite too. I'm going to save the ferrite for some other project. That's kind of a cute look. But really, I think I want this to stay flattish. Here are the two legs on the secondary. And this one is the common shared by both of the tubes, and this one goes to individual current limiting capacitors for the two tubes in this backlight. So I'm just going to destructively remove these connectors since they're kind of a pain to desolder. All right, I'm going to desolder the capacitors because I actually want to keep those. This would still work if you left the current limiting capacitors in, but it would work better without them. And we already have so much capacitance in the glass envelope of the neon bulb that I'm not really worried about limiting the current. These I still need to pull the pins out of. All the components on the secondary side are now removed. This seems like a good time just to make sure this inverter actually works. Right now the input power is 1.6 volts at 50 milliamps. That's about the minimum that'll actually strike a discharge in this tube. So I want to rewire this so that the two interior plates are both live with this high frequency AC, and there's kind of a ground exterior to the glass envelope. So I'm actually going to cut this wire that's leading into the cement so that I can electrically isolate the kind of screw base from the two filament plates. So I want to line this bulb up so that the plates are parallel to the board, and I also want the wires to run pretty much directly into the output of the transformer, so I want the wires connected to this trace here. I'm going to guess that that's going to be the front side. I think where the plates are closer to the glass envelope, I'm going to see more interesting interactions. This metal is really soft. I think it's a thin layer of brass, maybe. I think I've fussed with the edge enough. This is just some 20 gauge uninsulated wire that I'm going to use for mounting this. I have this little wire kind of harness that I've roughly bent into shape. I'm going to solder it so I can start to use this to mechanically secure the bulb. So I see an opportunity to use one wire here both to hold the neon bulb in place and to connect the kind of secondary high voltage ground back to the DC ground, which in this case is probably a good idea so that when you touch it, you don't get a zap. Here's the power input with the two unused wires, and then the spare connector. So if I just tie these three terminals together, then all of these are ground, and I can use that to ground the bulb up here. How's the bulb going to fit in there? Here I'm just bending the wire into a shape that holds the bulb nicely and also kind of sits well with the rest of the circuit board. And And I'm making sure the bulb is facing the direction I want it to face. So I want to solder that on the back. So this is not a sturdy mounting, but that's okay because it's going to be inside of a box. I'm gonna run one more piece of this kind of generic wire up from the circuit board to these two super delicate wires. And I'm just going to gently kind of push them toward the new little post I added. I want all these wires to come to a point at the same place because that's where I'm going to put the solder ball. I got lucky with soldering one wire, but the other wire is not really taking, so I'm just going to very gently wrap it and crimp it around the other wire. Cool, those two plate wires should both be connected to the central post. Let's power this thing up. Alright, so just like before, I'm going to be ramping up the voltage slowly. Oh, there we go. It starts pretty suddenly. So that was at about 6.5 volts. And then it doesn't fully extinguish until I get down to about 3.3 volts. Having that electrode right around the glass gives it a nice, intense, deep glow. Now the glass envelope is acting like the current limiting capacitor. The input power now is 6.8 volts at 50 milliamps. If I increase the capacitive coupling to ground by just touching the glass envelope, you can see the additional glow discharge, and this triples the power consumption. To get the full effect along the rest of the bulb, we'll need to add some additional grounding wires. And so that I can see what I'm doing, I'll be doing this with the power supply on. Now, if I were to touch that center connector right now, I would get a zap. This outside conductor is wired to the power supply ground, which is also connected to earth ground, and close to the potential of most things that I'll be touching. It's good to use really thin wire so that you don't block the neon tube. In this case, I happen to have some 40 gauge wire, which is incredibly little. The insulation on this wire won't really pose a problem for the high frequency, high voltage AC, but we do need to clean off one end just to make a good solder joint. I don't really like using super glue for this application, but I don't know if there's anything else that's really going to do the job. So I'm going to do the same thing that I did on the other flame effect bulb, and I just used small amounts of super glue on the back side to hold the wire right in the middle. That might be almost enough. Rather than solder the other end, actually, I think it's easier to get the tension I want if I just add a little bit of glue. Yeah, lots of plasma going on, nice big neon bulb. The oscillations in these tubes can take some time to kind of break in before they really look interesting, but this one's already getting started. I wonder if it responds to the laser yet. Oh man, my cat already knows what's going on. This is running at about 6 volts input. Alright, so now that's running at about 12 volts in the input. It's about a watt, which should be within the capabilities of both the inverter and the bulb. Oh, that's looking pretty good. I think the next step is to find a box to put this in and a power supply that can run it. So for the original flame effect, I used one of these small IKEA shadow boxes. I chose a matte white interior for this box because I really liked the way the light bounced off of it and created visible highlights. But for this next iteration of flame effect, I think I'll use a larger box to go with the larger tube. And I want to try a black interior to get the most contrast out of the neon. So I'm going to change this around so that the matte is at the front of the frame and then the spacer is right there. There are a lot of options for backing materials, but really I'm just looking for something that's matte black and that has a nice texture. Coal black drawing paper, which I found has a really nice look to it, and you can even draw on it if you like. I have plenty of ways to attach this, but I'm just going to try glue stick since I don't really want the mess of bringing out my can of Super 77 just for this. The bulb is going to be floating just barely above the backing here. Get some idea of what that'll look like. Alright, so I'm just going to add hot glue on the primary side of this circuit and attach that right to this backing. For powering this, I'm just going to use the cutoff end of a USB plug. This can just dangle out the bottom a little bit and run to another power cord. One advantage of running this thing off of USB is that it keeps the input power nice and low, so that there really isn't much opportunity for things to heat up. Sweet. 5 volts, 115 milliamps. Not bad. So it would definitely be possible to reinforce this by putting a bolt through right here. I think this might be fine with just the glue. Let's see if this holds. To get this wire out from the front side to the back side, I'm going to cut a little notch. There's usually one of these tabs that's off-center to make room for the hanger. Also make sure that the wire doesn't get hung up on any of these hangers. Just for some strain relief, I want this to double over before it goes out the bottom again. Let's just use some glue to secure these wires right here. That's totally what they meant when they said use the vise to hold it. I hope you enjoyed making this thing with me. Here's the original flame effect. Here's the new one we just built. And they're both running off of this little USB battery. I hope this video helped you find some inspiration for your own projects. If you liked it, check out some of my other videos. Also, if you have any ideas why the laser affects my other tube but not this one, then let me know. And if you subscribe, then you'll be the first to know when I post something new. See you next time.